Remember this beat-up old workhorse? I did the teardown and evaluation a while back, and there's a video if you want to check that out. In general, I'm quite impressed with how well this unit has held up to heavy commercial use. I had to replace only normal wearing parts. There were no heroic repairs needed. The machine is very durable and dead easy to fix. After reconditioning it thoroughly and testing it, I can say that I respect it and like it more than I thought I would. And here's a little paradox. It's uncomplicated, yet it's the most interesting grinder I've ever encountered. A lot of unexpected and oddly subtle design choices in here. One counterintuitive element is the design of the burrs, which I don't think is widely recognized. I found that burr alignment, which is a major focus of commentary on this machine, works differently from how the internet thinks it works. Alignment is not difficult, it's just commonly misunderstood. So get ready for a surprise when I show you how to align your EK burrs the right way. There was one design or manufacturing issue that I didn't like, secondary insulation on the stator windings, but I was able to fix that to my satisfaction with just a little effort and hardly any expense. If you saw the teardown, you know that this machine comes apart easily and logically. It's really designed to be serviced. While I had no trouble fixing it, in fact, I found it a real pleasure to work on. Buying parts was an exasperating ordeal. A straightforward job that ought to have taken a few hours, spread over a couple of days, took weeks. I was treated shabbily by the majority of Mahlkönig distributors and resellers I contacted for help with parts. Most simply ignored me even after I sent follow-up emails. In more than one language. They just don't seem to care about retail customers at all. Only 2 people actually tried to help from the start. Peter from Espresso Underground in the UK, who supplies parts for just about everything coffee-related and ships worldwide, and Josh from GH Grinding and Brewing in the United States. They are a distributor for Mahlkönig and various other grinders and other coffee-related kit, and they keep a great inventory of parts in stock. They really went out of their way to accommodate me. Espresso Underground and GH Grinding both deserve an award. You'll find links to them in the video description. Anyway, we've got a lot to cover. I'm going to show you the entire restoration from bits on the bench to a finely tuned machine ready for commercial duty again. Then I'll finish up with some taste testing of espresso, mocha pot, and pour over. So let's get on with it, shall we?
Oh my God.
It's like a miracle.
The first issue was some corrosion inside the motor housing. The 2 cast aluminum ends have got to fit the steel housing squarely to maintain concentric alignment of the bearing mounts, the bearings themselves, and the rotor shaft on the center line of the stator core. So these mating surfaces have got to be clean. I'm using a triangular file with ground edges, so it cuts only one surface at a time. I can clean the rim without gouging the shoulder and vice versa. You needn't buy such a file, simply make one. If you haven't got a bench grinder, a strip sander or belt sander will do. Next, I'll improve the stator winding secondary insulation. To prep the wires for overcoating, I'll clean them with isopropyl alcohol in a spray bottle. Magnet wire enamel is resistant to most solvents after it's cured. I've long believed that 99% isopropyl is about the best all-around solvent. I like this product, the Scotch 1601 from 3M. I've used it with good results many times. This will bond to the coating on virtually any magnet wire. I've masked the housing so that no overspray will collect on the rims here that I just cleaned, or anywhere inside the air gap. I removed some rust from the steel housing that I had complained about in the teardown video, but I've left the masking tape off those areas so that any overspray will help to seal the surfaces. It's not a perfect solution, but it can't hurt. I'll apply the lacquer in 6 or 8 light passes. We're not trying to drown it. This product is meant for touch-up and repair. Used more broadly, it will add mechanical strength for vibration damping, and it is a high-quality dielectric coating. In my experience, its only drawback is susceptibility to solvent attack. even after it's cured. So, in the future, if I want to prep it for overcoating after having used it once already, I'd make a test sample to check the solvent I'm planning to clean the surface with. After coating, I let it cure for a couple of days so that all of the solvent can evaporate. And now I'll remove the masking tape. You get a sense of how flexible this coating is. There's no flaking or even checking. It's a thin coating, as I said. There are some globs of resin on the surface of the stator core, but that's original, from the factory, and it's not harmful. I'm really pleased with how this turned out. The wire is coated nicely, and I'm confident that it's secure from vibration and friction. Here's the connection end before, where you can also see the rust, but more importantly, how dry the coil wires are and the voids between them. And now after. A big improvement. That looks great to me. And here's the non-connection end, the front from the operator's point of view, before spraying. You can see that there was some secondary insulation applied, and its thickness was decent in some areas, but not so much in others. Now it's well coated all around, and it looks really good to me. Those wires aren't going anywhere. Exactly what I was hoping to see when I opened it for the first time. Now the rotor needs a good cleaning. Never grind, sand, file, scrape, or otherwise attempt to alter the surface mechanically, because that can degrade performance. Remember, there are layers here separated by a film of insulation. You don't want to smear the edges together. That kind of defeats the idea of lamination, which is meant to discourage eddy currents and subsequent performance losses. I clean it with a degreaser to begin, and follow up later with a non-toxic chemical rust remover like Evaporust. And here's a sneak peek at the end result, which looks fine to me. I'm going to change the rotor bearings. These are 6004, which is a standard size. The inside diameter will be 20 millimeters, the OD 42 millimeters, and the thickness 12. There are 3 basic types: shielded, sealed, and open. Open ones are typically lubricated with oil, the others with grease. These are HCH brand, which I'm not well acquainted with. I think it's a Chinese outfit. I'm not sure that these are original. I expected ones by FAG, a German maker. These are shielded, meaning they have metal sides that make no contact with moving parts inside. I'm going to replace them with sealed bearings. These are very high-quality ones by SKF, a Swedish outfit, that are designed to handle both radial and axial loads. Just look up the spec sheet on these, the 6004 2RSL. You'll see that they're spec'd a lot higher than the demands they'll encounter here, both in terms of load bearing and speed. Because these are standard parts, you can use any brand you like. I prefer sealed bearings because they resist contaminants, moisture in particular, better than metal. High humidity all year round is an issue where I live. However, shields don't contact the moving parts, so those bearings can be quieter. The sealed ones I'm using might make more noise at high RPM, but in this machine, they'll run at 1/10 of the speed they are rated for, so I doubt that any sound difference will be noticeable. These have standard internal clearances, indicated by CN, or clearance normal. Top quality bearings this size should cost between $8 and $12 or euros or pounds each if you buy them from the right source. There's an interference fit with the shaft, but you won't need a press for a little job like this. Most people can use what they've got at home. Let me show you. First, heat the bearings gently. The inner race will expand, making them easy to fit. They should slide into place with a light tapping from a soft hammer or a sleeve of some type. You want to strike both races squarely or the inner race alone. I found the old distance bushing fits nicely and can be used as a little slide hammer on this end, and just tapping with it works well enough. Now, if there were an interference fit with the bearing housing and the outer race, you could chill the bearing in the freezer and again strike either both races squarely with a soft, flat hammer or the outer race alone using a sleeve or socket or what have you. In any case, you want to heat or chill the piece enough that you're tapping it into place, not driving it. Here's one of the old bearings opened up. You can see that the grease looks a bit dry. This is common in used shielded bearings. Grease is mostly oil with thickeners and some other additives to improve performance. Being mostly oil, it typically lubricates and bears weight the same way that oil does, with a hydrodynamic effect, creating a film that keeps two surfaces apart. If it becomes dry, it won't work as it should. A lubricating paste, on the other hand, contains very little oil. It's chiefly a powdered solid lubricant with a little oil serving as a vehicle to distribute the powder. The lubricating solids collect and reside in the microscopic low spots of wearing surfaces, burnishing them and reducing friction by direct contact. An important difference between paste and grease is that pastes can continue lubricating effectively even when the oil component has dried or seeped away. I'll go further into that later when I talk about manual lubrication and which products we should use for that. For now, I'll just say that I think the grease here is too dry for continuing use. Besides, the bearing felt a little crunchy with an axial load. I suspended the rotor by the outer race here and gave it a spin. You can test for crunch in the radial direction by bearing on it firmly and rolling it over a smooth, clean surface. If it feels anything less than buttery, replace it. It's a cheap part. Don't take chances. Now that we've got our new shaft bearings and a reconditioned stator, we're almost ready to install the rotor. But first, I'll need to measure the necessary clearances to ensure that this fan impeller won't scuff up the windings that I just worked on. You can move the impeller along the shaft, so you definitely want to double check. I'm locating the forwardmost surface of the windings and measuring from there to the rear bearing seat. I want to make sure that I've got that distance plus a quarter inch or so. I've set it standing like this because I want to measure from the bearing race, not the shaft, which protrudes slightly. I also need to be sure that it won't get snagged on one of these posts here in the front end. So, as they say, measure twice, cut once. I need to replace the felt seal for the motor shaft and its retaining ring. This is what prevents coffee grit from migrating into the motor. The felt needs soaking in pure mineral oil. It might surprise you how much liquid it can hold. The circlip here is actually the front bearing seat, and it needs to come out first. I didn't show this last time because I'd already recorded the voiceover, but there is some gouging in the bore here where the felt piece resides, and I kind of suspect it came from a broken mainspring, which gives you an idea of how tough this baby is. When something is old and has been used hard, you get to see what it's really made of. I did have to dress that inner surface so that it wouldn't snag the new retaining ring, but it wasn't a big deal. I cleaned it up with a scalpel. I recorded it, but my hand blocks the entire operation, so sorry about that. First, in with the oiled felt ring, and then its own little retainer. If you have a socket the right size, put an extension on it and push. Don't put too much pressure on the felt. Don't hammer it. You want to compress it a bit and see a little oil squeezing out, but not a lot. Now I'll replace the circlip or snap ring that seats the bearing. Finally, I'll put a light smear of lubricating paste on the inner surfaces of the bearing mounts so that they'll go together and come apart without a struggle. And some lube on the spring washer that pushes the shaft toward the rear seat. Basically, you want to lubricate anything that bears against anything else or rotates inside of or around anything else. I'll get into lubrication later. Right now, I want to keep things fairly clean so you can see what I'm doing. Now, with that sorted, it's a simple matter of lining up the two ends such that the threaded rods pass through easily. On the connection end, be sure to tuck the leads behind the coil so that the way is clear. You won't need a torque wrench for this, but be mindful of the need to tighten in stages and apply roughly the same torque to each fastener because we need both ends seated squarely. The grind chamber geometry is determined by the alignment of the two bearing housings. They should be concentric with the stator center line, and their sides should be perpendicular to the deck of the stationary burr. Before I move on, I'll measure everything and see where we are and make a note of it. The faceplate, which houses the adjustment spindle and bearing, mounts flush on this edge, so I want this edge parallel with the stationary burr carrier, the deck here. That way, the front bearing and adjustment mechanism will also be concentric and parallel with the stationary burr. so I'll measure the depth from the edge to the deck at several points. And that looks excellent, almost perfect. So we have a really flat plane to work off of here. This doesn't guarantee that the motor shaft will be perfectly perpendicular, but it's a good start. Next, let's see how much runout there is on the shaft. And yeah, 2/100ths of a millimeter, or less than a thou, around 8/10,000ths. Really, it doesn't get any better than that, so this is promising. I've got a test indicator mounted on the shaft. It's just a little jig that I made, fitted into the kerf there with a very strong magnet keeping it level. This shows the shaft out of perpendicular alignment by 3.5 thousandths, or nearly 1/10 of a millimeter. I've noted the apparent low spot with a single mark and the high spot with a double mark. That way I won't forget. So there must be a little angle discrepancy between the sides of the bearing housing, which aligns the rotor shaft on the other side, and this grind chamber deck. However, this is hardly the ideal place to anchor the test indicator. Its distance from the center line of the shaft will give you an exaggerated measurement. If it's out by 3 thousandths measuring from here, it's probably out by half that or less in reality. But we'll come back to this later. Let's continue assembling. Here's the faceplate, which houses the grind adjustment spindle and its bearing. The spindle is in excellent condition, so it's going right back in, and the bearing and seats are okay, although the surface facing the rotary burr carrier was a bit scored. So to make this machine suitable for commercial use again, I decided to replace the bearing and seats. I wouldn't bother if I aimed to keep it for myself. Heat the bearing and tap it into place. A flat, soft hammer that contacts both races squarely is ideal, or a socket or sleeve that catches only the inner race. Your choice. There is a felt ring here, but it's a different size and design from the one on the motor shaft. This seals around the bearing and prevents coffee grit from migrating into the adjustment threads. The felt is denser, more compressed than the other one. You get a generous piece and just cut it to fit. Get it seated, then apply pure mineral oil, which it will absorb greedily. Try again an hour or so later, and it will probably take a little more. Once that's done, tap the bearing assembly into place with a soft hammer. Now I want to talk about lubricants and thread compounds. It's a pity that this machine requires manual lubrication. Paste lubricants are messy, attract coffee grit, and complicate maintenance and cleaning. This is far less of an issue for home use, but in a commercial setting, you've got to stay on top of it. You'll need a lubricant that's non-toxic, capable of bearing high-pressure loads, with a nice adhesive quality so it stays put on rotating parts. I'm a fan of Mahlkonig 1000, which I use in automotive and non-household applications, especially as a thread anti-seize compound. I don't like it for household use because it has distillates and contains copper, which doesn't work and play well with stainless steel parts or fasteners due to galvanic potential. Around the house I like G-Rapid Plus, a paste which has very low toxicity and contains graphite and molybdisulfide powders. It's not certified for use with food, but the MSDS makes me think that it's less toxic than some that are certified. There's no aluminum, nickel, or copper, so it's perfectly good for stainless fasteners, and it has exceptional load-bearing strength. Unfortunately, it's nowhere near sticky enough. It lacks the adhesive property that we need in this application, and it's incredibly messy thanks to the powdered graphite. A tiny bit of it will leave traces everywhere, so you'll want to use it only where it won't spread or creep. I find it's an excellent thread compound. There's also Mahlkonig P37, which is excellent and contains zirconium dioxide, which provides a little grit that keeps the threads clean in hostile environments, exhaust manifolds, for example. You know I always try to recommend less expensive alternatives for you, so I hate to admit this, but the Kluber 84201 that Mahlkönig recommends does tick all of the boxes. Low toxicity, high pressure performance, no issue with stainless, and most importantly, it's nicely adhesive, really sticky, so it tends to stay where you put it. It also looks relatively clean and tidy. It's just that Mahlkönig sells a 60-gram tube for €70, which I consider a criminal offense. I pay around €25 from my source, so I would suggest that you check with industrial suppliers in your area. If you can get it for a fair price, I recommend it strongly. I don't know of a product that's better suited to this application. Now, I have seen internet people using this type of silicone lube, Mahlkonig 111, which is certified food safe, but is absolutely unsuitable for the EK43. It has no real load-bearing strength. It doesn't contain any solids. Its main purpose is to lubricate and preserve synthetic O-rings and seals, which it does remarkably well, and it's also a good dielectric grease. I use it regularly for O-ring duty, and I really like it. But as a load-bearing lubricant, it's useless. You'd be better off with Vaseline. I think the shear plate installed here was the wrong one, meant for the aluminum burr carrier. This carrier is steel, and it needs a slightly heavier, stronger one. Of course, one that's too tough is worse than one that's too weak. I'm using a posh brass replacement that I got from GH Grinding in the States, for a bit of style. Not that anybody'll see it. They have brass ones for the aluminum carriers too, but they're not the same part. Now I want to change out this dial decal, which I find ugly. I'll just warm it with the heat gun to soften the adhesive and clean the surface thoroughly with isopropyl alcohol. I have a white on black replacement here that I think looks pretty classy. It's got tabs, I imagine to accommodate a later model, which I'll cut off. First, I'll use the adjustment knob to find the farthest clockwise position and line up the decal's 0 mark there. Once I know where I want it, I'll tape it in place, double-check the fit and alignment, and then remove part of the backing to anchor it. And there we go. I like it. Big improvement, I think. I'm going to wet sand the knob to get rid of the gloss, which I don't like, and paint the pointer so that it's easier to see. I haven't decided which color yet, so I might not have it done in time to show you today. I won't repaint the grinder overall, as I don't want to deceive anyone. It's an old machine and it should look it. I would like to replace the 2 red decals, because I think the old girl has earned them, but I couldn't lay hands on them. Now let's set this monster up by aligning the burrs so that they're concentric and parallel. Based on some of the internet sources I've encountered, I sense that there's a lot of popular misunderstanding going around. So let's take our time here and find out how this all really works. I'll start with the stationary burr. The deck is flat, as we discovered, but the rotor shaft is not quite perpendicular. I measured a difference of about 3½ thousandths, or roughly 1/10 of a millimeter, between the apparent lowest and highest spots. But the indicator was overhanging the center by quite a distance, which means the discrepancy is probably tiny and possibly negligible. If you look at this jar that I'm using as a stand, when I tilt it by placing a coin under one side, then measure near the side, I see something like 124½, 125 millimeters to the lower edge. Now out here, I'd call that, 127. So a 2½ millimeter difference. So that's the type of error we're dealing with. Normally I like PETG plastic shim stock for light-duty applications like this. It's color-coded and very convenient. But aluminum foil is fine for this application. For more heavy-duty applications, steel or stainless steel is best. Most of you will be using foil, so I will too. It comes in various thicknesses, usually not mentioned on the package, so you'll have to measure it. As it turned out, I could use a 1/1000th shim. That's about, 25 thousandths of a millimeter, or 25 microns. Maybe half the width of a typical human hair. The difference it makes is barely measurable, and the effect will not be noticeable because there's more play than that stacked up in the shaft bearings and carrier bore. 25 microns either way is absolutely undetectable on the pallet, except by triggering a placebo effect. So I can use a shim or not. I actually decided to leave it out. It's the rotary burr we need to worry about. I'll center the stationary burr using a drill shank, which makes a great feeler gauge for concentric circular surfaces. Put a little torque on the screws, just enough so that there's a bit of drag on the burr. This one is 5.5 millimeters and it feels a bit loose. This one is 5.6 millimeters and it fits just right. So tighten the screws once you feel the same amount of friction all around. This entire housing is well made, so working off the side here is good enough, especially with such wide flats as these burrs have got. Of course, the rotor shaft would be the best reference, and Mahlkönig sells a tool that works off of it. If you repair these for a living or own a bunch of them, it might be worth having. Now for the rotary burr, which is a very different animal. We don't want to get obsessive about this one either. I think people get confused by the difference between clearance and tolerance. So let's be clear. Clearance is the appropriate distance between two parts. Tolerance is the maximum value by which that distance can deviate from the design spec. If the clearance is, say, 6 thou, then that's a generous distance. But if the tolerance is plus or minus 1, then you pretty much have to nail that 6 thousandths. An everyday example would be the main bearings in your car. There has to be a wide enough gap between the crank journal and the bearing shell for motor oil to provide adequate lubrication and load bearing. That's an example of clearance. Meanwhile, that gap's width and shape have got to remain strictly within a specified range. That's an example of tolerance. A crankshaft isn't a tight fit, but it is a precise one. This machine was built to precise tolerances. That is, the design specs are followed pretty rigidly. However, it also has generous clearances, meaning that while the parts are fitted precisely, they are not always fitted tightly, because it's an industrial machine. It works hard. It gets hot, often unevenly. Parts expand, often at different rates. You need room for that to happen. Too much clearance, all right, you'll get accelerated wear. Too little, and you get heat damage and possible seizure. Generous clearances are engineered into this machine with good reason. This is a really important point. The large clearances mean that no matter how precisely you align these burrs on the bench with no working load on them, as soon as you begin grinding coffee, they will be deflected by the beans and your micron-level alignment goes right out the window. The single slackest element is the rotary burr carrier. The stationary burr is rock solid, but this one both rotates and adjusts for distance, which means it chatters and wobbles under the stress of doing its work. The coffee exerts force. It deflects the burr, and it does so with a lot of leverage because the burr is so big. This is true of all grinders, but it's especially true of the EK. Think of that long radius of 49 millimeters as a lever that the coffee beans push against. If one of the burrs is going to rotate, there has got to be some play. If the gap between the burrs is adjustable, there has got to be still more play. And if the machine is heavy-duty and heats up during normal use, there has got to be even more play on top of that. This is not a Swiss watch. 0.05 of a millimeter up to 0.1 of a millimeter is a perfectly respectable standard to shoot for. You can be sure that the rotary burr will be deflected farther than that during normal use. But that deflection also means that the rotary burr is, to a certain degree, self-aligning. There's enough movement permitted that the coffee can apply a relatively even force all around, keeping the rotary burr fairly parallel to the stationary one. So the slack in the rotary carrier is not nearly as bad a thing as people believe. In fact, it's something you can and ought to exploit for alignment. Look at this. The carrier boss contacts the faceplate bearing. We've already established that the faceplate will be nicely parallel to the stationary burr. We've also noticed that the shaft angle is off by a negligible amount. The force of the beans flowing through should cause these two surfaces here to meet flush if there's enough play in the bore to allow it. So the big question is not how perpendicular is the shaft and how do we keep the carrier centered on it perfectly, as I think most people assume. The real question is how parallel are these two surfaces? I'm going to show you how to make minor corrections based on this relationship. assuming your machine is similar to mine. It's possible that more recent ones might have too little clearance to take advantage of this, but I rather doubt that. Excessive clearance in this carrier bore still draws a lot of complaints online. I'll set the old bearing and bearing seat on a flat surface. The new parts are already installed in the faceplate. I'm going to measure the height of the surface of the burr and later shim it and bring the burr flats into position parallel to the bearing seat, which we know is parallel to the stationary burr. We can see that the distance is a bit off, so I'll mark the low area and shim it. And now with that done, we can see that the plane of the burr flats and the plane of the carrier boss and bearing seat are all parallel with each other. Our previous measurements showed that the bearing seat will be parallel to the stationary burr, so if we're getting consistent readings here, the burrs must be parallel to each other, which I'll just verify with the ink test. This time, I'll run the machine normally using the front cover with the new replacement bearing and seat rather than turn it by hand. And the ink has been wiped from all around the flats. There's still plenty in the troughs, but the surfaces are quite clean. I hope you can make that out. This persuades me that there is enough play in the carrier bore so that the flow of coffee will force the rotary carrier against the faceplate bearing seat, which will then overcome minor burr misalignment. Assuming that my machine isn't abnormal, I think that using this relationship between the plane of the carrier boss and the burr surface is the right way to visualize and correct the alignment of the rotary burr. I think I can demonstrate the self-aligning nature with this audio sample. What you hear is an epicycle. Imagine this burr turning at 1400 RPM and tilting slightly. You get a slow, regular cycle of the touch point rotating. This couldn't happen unless there's enough play in the carrier bore so that it can be aligned by the force of the beans pushing the rotary carrier boss flush against the faceplate bearing seat. So long as that relationship is good and the misalignment is minor, this grinder aligns itself during use, when it actually matters. I'm sorry to say that all the effort and debate and anxiety surrounding precision burr alignment on the EK43 has been so misleading, but there it is. The machine is better than you think. As for doing this the wrong way, I've heard about a destructive method of alignment using numerous grades of abrasive paper stuck onto the burrs with adhesive and using the rotary carrier as like a sanding block or something. This will make permanent changes to the stationary carrier, the deck of the grind chamber, and that is a bad idea. The stationary carrier is precisely machined and is the last thing I'd want to risk damaging. As we saw, the rotary carrier is a bit loose on the shaft, so why would you use that to establish the degree of precision for the job, especially when you're making permanent changes to another part that's been machined with care? You're damaging a precision part to make it compatible with a less precise part. And why would you spend hours cutting sandpaper rings and changing them for finer ones and repeatedly dismantling it and cleaning and fiddling with adhesives at every step while allowing loose abrasive grit to migrate into your grinder's internals and ultimately risk going too far and ruining the entire front housing assembly? And what is the point of progressively finer abrasive grades? You're supposedly correcting it, not polishing it. This just reeks of amateurism. Stick with shims. They're quick and not destructive. You can undo them and redo them as often as you like without the slightest risk, which is why professionals use them. I promised there would be a surprise, so get ready. These burrs are quite unusual, a truly unique design which I don't think is fully appreciated. If you look at the auger and the direction of the spiral, it's obvious that the coffee will feed properly only if the rotary burr turns clockwise from the operator's point of view. But that means the relative movement of the sharp edges on the flats will be counter to our expectations. I'll demonstrate using this pair because they're big and the features are easy to see. There are sharp inclined edges which cut the coffee particles. The way this one rotates means that the blades face each other and act a bit like shears, attacking the coffee, so to speak. And that seems right intuitively. Every grinder I've owned uses this arrangement. It's like the teeth of a file, which are inclined so that it will cut in one direction. It won't work with the sharp edges moving away from the workpiece. In fact, drawing it backward is a bad habit that can blunt the teeth. Not to be confused with draw filing, which is a sideways move that I'm not getting into today. The EK43 burr rotates counterintuitively so that the flats behave as if I were holding two files and moving one of them backward above the other, instead of having the sharp edges move into the coffee. It's as if the flats are burnishing the coffee particles, only that's not right because they don't end up rounded as you might expect. They have nicely irregular and random shapes, which I always take as a good sign. The blades here have a more conventional profile, but they're not terribly sharp. These two long ones face the coffee squarely, like hammers. The flats are unusually wide and have very sharp edges, but they're inclined away from each other. I think the dynamic where those edges encounter the coffee is more like a scraper than a burnisher, but I'm guessing. I told you this machine was interesting. Straightforward, uncomplicated, yes, but quite interesting. Now let's look at the grind performance. I want the knob to turn from lock to lock and describe a full range of coffee sizes, from coarser than I would need for French press to finer than I would need for espresso, and that's just what I've got. The widest setting, number 16 on this scale, is coarser than I would use for anything. 12 looks about right for French press, and 10 to 8 for drip. What I really like in all these samples is the predominance of sharp, irregular particle shapes and plenty of fines. Angular bits expose more surface area, so you get a nice range of flavors out of the coffee. I'm not sure how these burrs managed to produce this result, but I do approve. It does feed the beans very fast, and later models seem to have more turns in the auger to slow the feed rate a bit. You could buy one of the newer carriers, or you could just do what I do, open the gate valve slowly. I like to look at the aftermath of a pour-over. I have a standard test setup. These are both 30 grams of the same coffee, 450 milliliters of water, with the grind sizes dialed in and timed for exactly 4 minutes with Hario boxed white filter papers. This sample comes from the new Niche Duo fitted with brew burrs, so one's designed specifically for this. I like to sieve out the boulders for this test, chiefly to remove the chaff so that we can see the surface better. Interestingly, both grinders produced the same amount, to 1/10 of a gram. The Duo coffee looks as you would expect, a very modest scattering of fines, maybe not quite enough for my taste as I like the bitter sweetness. And the EK looks almost exactly the same. The proportion of fines to larger particles is virtually identical. Flavor-wise, I have to give a slight edge to the EK, but they're both very good. For espresso, I was able to pull chokers using the 0 position, even with very hard beans, so there's virtually no chance I'll have to recalibrate it for espresso, regardless of the coffee. I was able to get good shot times from positions around 1.5 down to near 0, depending on the coffee. It is a little touchy dialing in, so you might need to adjust your usual dose now and again. Some people report problems making espresso with the EK, but I really haven't run into any issues. The mocha pot worked out well in the 7 to 5 range. It's pointless to show you those finer grit sizes because you wouldn't see any detail, but I can say that the range here with one full turn will let me use this as an all-around grinder without making any further adjustments. I'm not testing Turkish coffee because the machine has optional burrs for that, so it struck me as unfair to test it with these general-purpose ones. In all samples, I thought the flavor was excellent. Very complex, a lot of range. Based on flavor alone, this might be my favorite grinder by a small margin. I mean, they're all good, so ask me again in 3 months' time. Those who saw the teardown know that the original burrs received some unusual treatment. This looks like a cowboy repair to me, addressing what problem, I'm not exactly sure. Taste testing answers the question of whether the burrs are still good enough. They're just fine. So what about you getting one of these? If you're a commercial buyer and you need a durable, competent bag grinder that can handle a range of grit sizes, this would be a fine choice. In the cafe, workflow is an issue. In a situation where single dosing works for you, this would also be a fine choice. For home use, I don't see the point. I suppose it has a certain brutal charisma, but it takes up a lot of space. Even the shorter S model. It weighs about 25 kilos or 55 pounds and can cost as much as 3,500 euros, which for a lot of people means marrying it. This might be the only grinder they can afford for several years. But with all the R&D going on these days, new designs are coming out with greater flexibility and convenience in terms of workflow, with simpler maintenance in smaller, quieter, tidier packages. Those are all features you might appreciate, if you weren't already married. The overcapacity here is comical. It's able to grind 20 grams a second, so you'll be running it under a load for, 10 seconds a day maximum? The stock burrs are good for 6,000 kilos of coffee, or 13,000 pounds, or 6 million grams, nearly a million single shots. And home users are still buying these coated aftermarket burrs for $500 to $1,000 extra so they can grind, 12 million grams? Am I the only person who understands this as preposterous? Suppose you pull the equivalent of 4 double shots a day, every day, without exception. In that case, it will take you 685 years to max out the stock burrs. Or, to look at it another way, you'll want to replace them now if you had started using them in the year 1338. As for me, I definitely respect the machine. I like the coffee I make with it, and I intend to keep it for a while, especially because it's a great teaching prop. But for you home users, I think you'll be better off with a more flexible and agile machine, one that's designed for the future, not built for the apocalypse. Well, that's about all for today. Coming up, I have a very nice hand grinder to show you. I will probably post a detailed rant about the exasperation of dealing with Mahlkönig as a retail customer, things you should know if you're thinking of buying one of their units. I also took a comical trip down a rabbit hole with the EK involving the direction of rotation and motor wiring, which led me to a crazy place. It was pretty funny, and I'd have loved including it here, but this video is already too long. I've also got an announcement about the channel, so keep in touch. Cheers!